Most people think gold is discovered in a moment of luck, a flash in a pan, a glittering surprise pulled from a riverbed or cracked from a rock. But that belief hides a much deeper truth. Gold is not found by chance. It is released by process. Long before gold becomes a bar in a vault or a hedge in an investment portfolio, it exists locked inside stone, compressed, fractured, and hidden by forces that operate far beyond human timescales. And those who understand this process don't just find gold. They understand value before it becomes visible. This story does not begin at the surface. It begins underground, where gold is not free, not shiny, and not valuable to anyone who does not know what they are looking at. Gold ore is not gold as most people imagine it. It is rock that has been changed, chemically, structurally, and economically, by geological pressure. The gold inside it is often microscopic, bonded to quartz veins, sulfide minerals, or iron-rich host rock. To the untrained eye, it looks worthless. To the trained eye, it is stored potential. This is where geology quietly becomes finance, because every step required to pull gold from ore mirrors how wealth itself is created, not quickly, not loudly, but methodically, patiently, and with an understanding of systems. Gold does not appear randomly inside rock. It is introduced deep underground. Hot fluids move through cracks in the Earth's crust. These fluids carry dissolved gold atoms, so small they cannot be seen, so dispersed they are meaningless alone. When pressure drops or chemistry changes, those atoms precipitate. They settle into fractures, along quartz veins, or inside sulfide minerals like pyrite. This is the first trap, and every trap creates concentration. Ore exists because something slowed the system down. A fault line, a temperature gradient, a chemical boundary. In finance, wealth forms the same way. Capital flows constantly, but it only accumulates where friction exists, where something interrupts movement and allows value to settle. When prospectors break open gold-bearing rock, they are not finding gold. They are revealing where the earth decided to stop moving it. The first step in pulling gold from ore is recognition, knowing the difference between barren rock and host rock, understanding texture, color, and structure. Quartz alone means nothing. Iron staining alone means nothing. But patterns do. Gold-bearing ore often shows signs of stress: crushed quartz, brecciated rock, angular fragments cemented together. These are not random. They are evidence of violent geological events that created space where gold could enter. This matters because value always enters where structure fails. Once ore is identified, the process becomes physical. Crushing the rock is not about brute force. It is about liberation. Gold cannot be extracted until it is separated from what holds it. In small-scale prospecting, this means breaking ore into gravel, then into sand, then into powder. Each stage increases surface area. Each stage exposes more gold, and each stage reflects a principle investors understand instinctively. Value must be accessible before it can be realized. Locked value is not wealth, it is potential. Historically, entire economies were built on this step. Stamp mills, ball mills, crushers powered by water, steam, and eventually electricity. Not because gold was rare, but because accessing it was expensive. The difficulty of extraction is what preserved its value. This is why gold still matters today. Modern investors often focus on charts and prices, but the price of gold has always been anchored to one reality: it is hard to get out of the ground. No technology has ever changed that. We can refine faster, transport easier, trade globally, but the extraction step remains slow, energy-intensive, and limited. When you crush gold ore, you're participating in the same constraint system that central banks quietly respect. After crushing comes separation. Gold is heavy, extremely heavy. It does not behave like most materials. In water, it sinks aggressively. In motion, it resists displacement. This is why gravity separation works even at small scales. Panning is not primitive. It is physics. The same principle used in modern processing plants applies in a pan. Density sorting. Gold settles. Waste moves away. This is where patience becomes measurable. You cannot rush gravity. You cannot argue with density. The pan rewards controlled movement, not force. Investors who survive long cycles learn the same lesson. Aggression increases noise. Precision increases yield. In many gold ores, however, gravity is not enough. The gold is too fine, too chemically bound. This is where the story becomes more complex and more revealing. Gold often hides inside sulfide minerals, especially pyrite. To release it, those minerals must be broken down. In industrial settings, this involves roasting, pressure oxidation, or chemical leaching. In small-scale settings, careful grinding and selective processing. The important point is not the method. It is the reality that gold resists release. It does not want to be free. This resistance is not a flaw. It is the reason gold retains monetary relevance centuries after its discovery. Every ounce of gold represents not just rarity, but accumulated effort, energy, time, risk. This embedded cost is what makes gold different from currency created by policy or code. When investors allocate to gold, they are not betting on excitement. They are acknowledging friction. Gold ore teaches this lesson directly. Most rock yields nothing. Some yields trace amounts. A few yield enough to justify effort. The ratio never changes. Only the tools do. Understanding how gold is pulled from ore changes how you see markets. You stop chasing surface shine. You start looking for structure, for traps, for systems where value accumulates quietly while attention is elsewhere. In the world of gold recovery, some methods are so overlooked, so simple, that they almost sound unbelievable. Today we journey into one of the most natural processes of all, recovering gold using nothing more than boiling and cooling. No acids, no toxic chemicals, no heavy industrial equipment, just fire, water, time, and patience. But as easy as it sounds, this process hides secrets that only reveal themselves step by step. If you miss one stage, the gold remains locked, concealed in the rock and sand, mocking your efforts. But if you follow carefully, what begins as dull material could transform before your eyes into shining fragments of treasure. Imagine standing by a riverbed where quartz veins have shattered and released their contents into the sand. You scoop up a handful, and hidden within that dirt lies the ancient legacy of molten earth. The challenge is unlocking it. Boiling and cooling may seem too gentle to extract such a stubborn metal, but when done correctly, it can coax the gold to separate itself naturally. And so the process begins. First comes collection. Not all material responds to this technique. You must start with ore that carries free milling gold or fine particles mixed with quartz, sulfides, or black sands. The sharp eye picks samples that sparkle faintly under sunlight, tiny flecks of metallic brightness or streaks of quartz threaded with iron staining. Each handful is a gamble, but within the right stones lies the reward. Now preparation. Rocks and sands must be reduced. Crushing is essential. Without acids or chemicals, you rely on heat and mechanical breakdown. The hammer, the mortar, the grinding stone, these become your tools. The ore is pounded into smaller fragments and then into dust fine enough that gold can be released during the boiling cycle. With every strike, the grains carry with them the story of mountains formed millions of years ago. Once the material is ready, the water is brought to life. A fire is lit and a pot of water set to boil. Here lies the simplicity. Water, the universal solvent, when pushed to its limits of heat, can reveal surprising properties. As the ore is introduced into the rolling boil, the fine particles scatter, suspended in turbulence. Gold, being dense, begins to behave differently than lighter minerals. At first it seems chaotic. Clouds of dust, rising bubbles, fragments colliding. But patience reveals order. The lightest silicates and sands stay aloft, carried by the motion of boiling water. Tiny iron oxides may remain suspended, discoloring the water with rusty tones. But the gold does not drift. It sinks, resilient, enduring the chaos until it settles at the bottom. Then comes the waiting. The boiling continues, and with it, the separation sharpens. This is not a quick trick. It is a gradual purification. The repeated cycles of rising bubbles and swirling currents work like nature's own sluice, shifting lighter materials upward and forcing heavies downward. If you scoop prematurely, the results vanish. But if you trust the method, the precious metal begins to stand apart. And when the boiling ceases, the next phase begins: cooling. It is during cooling that the most dramatic transformation can occur. As water slowly surrenders its heat, convection currents calm, and particles find their final resting place. The lighter minerals drift toward the top or remain in suspension, while dense fragments, including gold, form a concentrated layer below. The once chaotic mixture grows still, like a hidden message revealed only when the noise fades. Cooling can take minutes or hours depending on the volume. Some practitioners accelerate it with cold stones or by pouring into secondary containers, creating thermal shocks that drive further separation. Imagine dipping a glowing hot stone into icy water, the cracking, the release, the sudden currents. In that turbulence, stubborn particles shake free, and gold becomes more defined in its resting place. When the vessel is still, the suspense peaks. The surface is skimmed, removing floating silicates, organics, and foam. Beneath lies clearer water, and at the bottom, a gathering of dense material. It may not look golden at first. Black sands, magnetic iron, and other heavies often cloak the treasure. But within that dark bed lie the particles of gold, waiting for their reveal. At this stage, the process repeats. The material can be decanted and reintroduced into boiling water again. Each cycle sharpens the separation, stripping away unwanted companions until only the heaviest remain. Boiling and cooling act like nature's heartbeat, contracting and releasing, each pulse driving the gold closer to purity. What follows is the final unveiling. The concentrate is carefully poured, leaving behind the densest fraction. Sometimes it glitters immediately, tiny yellow specks gleaming among darker grains. Sometimes it hides, demanding panning or gentle blowing to uncover. Either way, the moment of recognition carries the thrill of discovery. You began with rough ore, and through nothing but fire, water, and patience, the gold has shown itself. This method, while simple, carries a deep scientific truth. Gold resists chemical alteration, refuses to corrode, and clings to density as its greatest ally. By using boiling and cooling, you're harnessing physics itself, the contrast between density, temperature, and motion. You're not forcing the gold out. You're letting it choose its place, and its place is always at the bottom. And so the cycle continues. Each attempt brings refinement. Each batch of ore reveals its secrets slowly. Some yields are modest, flecks barely visible. Others shock you with their richness, clusters shining like starlight trapped in stone. But always the process is the same: fire, water, time, and trust. In the end, what begins as a suspension of dust becomes an undeniable truth. Gold is stubborn, but it cannot hide forever. Through boiling and cooling, the metal's ancient resilience becomes its undoing, and what was once locked in rock rests in your hands, gleaming with quiet defiance against the centuries that tried to bury it. This is gold recovery at its most elemental. No laboratories, no poisons, no machines. Just the raw forces of nature, replicated by human hands. The method is slow, but the reward lies not only in the metal itself, but in the timeless connection between Earth's hidden treasures and those patient enough to uncover them. And when the final particles are gathered, shimmering in the pan, you understand what few ever will, that even the simplest forces, boiling and cooling, hold the power to unlock the eternal brilliance of gold. And so, from fire to water, from boiling chaos to cooling stillness, the story of gold unfolds once again. A story as old as the earth itself, revealed through nothing more than patience and the simplest forces of nature. What began as ordinary rock has now left behind its shining truth. But remember, this is only one path among many. Gold is never easy, and the earth never gives up its secrets without a test. Every method has its challenges, every rock holds its mystery, and every attempt pushes you closer to unlocking the treasure beneath your feet. When most people see rust, they see damage. They see neglect. They see something that has already lost its value. But beneath the surface of the earth, rust is not a sign of loss. It is a signal, a chemical message written slowly by water, oxygen, pressure, and time. A message that geologists, miners, and serious prospectors have learned to read with precision, because rust does not appear randomly. It forms where reactions are active, where minerals are breaking down, and where something deeper is happening beneath the rock. And in certain geological environments, rust is not the end of a process. It is the beginning. Long before gold is seen, long before quartz veins are exposed, long before any metal reaches the surface, oxidation begins its quiet work. Iron reacts, sulfur shifts, invisible fluids move through fractures that most eyes never notice. What rises to the surface is rust. What stays below is often far more valuable. This is why experienced field geologists do not dismiss rust-stained rocks. They stop, they look closer, they ask a different question. Not, why is this rock damaged? But what process created this pattern? Because rust patterns are not uniform. They spread in halos. They follow fractures. They bleed downward. They stain certain rocks and ignore others entirely. And every one of those behaviors carries information. In arid regions, where rain is rare and surface erosion is slow, rust becomes even more meaningful. Oxidation there is not constantly washed away. It accumulates. It records history. A rust-stained outcrop in a desert is often a long-exposed window into subsurface chemistry. It shows where fluids once traveled upward from depth, carrying dissolved metals with them. It reveals fault zones, shear zones, and ancient hydrothermal pathways that no modern map clearly shows. This is why some of the richest gold systems in the world were first identified not by gold itself, but by iron oxides at the surface. Gold, unlike iron, does not rust. It does not oxidize. It survives intact while everything around it breaks down. But gold rarely travels alone. It is often carried by hot, mineral-rich fluids rising from deep within the crust. Those fluids interact with iron-bearing minerals along the way. They alter them. They destabilize them. When those systems collapse and cool, iron minerals oxidize near the surface. Gold remains behind, trapped in veins, fractures, and chemically favorable zones. What you see on the surface is rust. What you don't see yet is the system that created it. This is where most people make their first mistake. They treat rust as contamination. They treat it as surface noise. But in geology, surface features are rarely noise. They are compressed summaries of deeper processes. A wide rust halo often indicates prolonged fluid flow. A sharp rust boundary may point to a structural control. Patchy, mottled rust patterns can signal brecciated rock where fluids once surged violently through broken stone. These are not random stains. They are maps. And once you learn how to read them, you begin to realize something important. Gold is not evenly distributed in the earth. Neither is rust. They cluster. They follow rules. They respond to structure, chemistry, and time. In many gold-bearing regions, iron sulfide minerals like pyrite form deep underground alongside gold. When erosion exposes those rocks to air and water, pyrite breaks down. It oxidizes. It produces iron oxides, rust, and acidic fluids. Those fluids may dissolve surrounding minerals, enlarge fractures, and even free microscopic gold particles that were once locked inside sulfides. In some cases, rust zones mark areas where gold has already been liberated and reconcentrated just below the surface. In others, they mark the weathered cap above deeper, untouched ore. This distinction matters because not all rust means gold, but almost all significant gold systems leave some kind of oxidation footprint. This is why serious prospectors do not chase shiny colors alone. They chase context. They ask whether the rust is aligned with regional structures. They check whether it follows a fault or shear zone. They observe whether quartz is present, whether the rock fabric is fractured, whether the rust penetrates deeply or only coats the surface. They understand that rust is not the prize. It is the invitation. And this is where geology quietly intersects with wealth. In financial markets, most people react to surface signals. They chase headlines. They respond to price movement. But long-term wealth is rarely built by reacting to what is obvious. It is built by understanding systems beneath the surface. Gold, both as a metal and as an asset, rewards patience and structure. It forms slowly. It concentrates quietly. It reveals itself only to those who understand process, not appearance. Rust patterns work the same way. They are slow signals. They do not scream. They whisper. And those whispers have guided generations of geologists toward discoveries that reshaped regions, economies, and lives. In the American West, countless gold systems were first traced by iron-stained ridges cutting across otherwise ordinary terrain. In Nevada, Arizona, and parts of California, oxidation zones stretching hundreds of meters wide marked buried systems that would later become major producers. In these places, rust was not the end of value. It was proof that value had passed through. And once you begin to see rust this way, you stop ignoring certain rocks. You stop walking past certain outcrops. You stop dismissing what looks ugly, broken, or worn. Instead, you begin asking better questions. Why does the rust thicken here? Why does it fade there? Why does it follow this line but stop abruptly at that boundary? Those questions lead downward, and downward is where gold lives. This is not about romantic treasure hunting. It is about reading physical evidence left behind by natural systems far more powerful than any machine. Oxidation is chemistry in motion. Rust is its signature. And beneath that signature, in the right geological setting, lies a story of pressure, heat, fluid flow, and concentration that can turn ordinary-looking ground into extraordinary value. In the next phase of this story, we move deeper, from surface stains to subsurface traps, from rust patterns to the exact conditions that determine whether gold stayed, moved, or concentrated. Because rust is never the answer by itself, but when read correctly, it tells you exactly where to look next. Once rust has drawn your attention, The real work begins beneath the surface, because oxidation is only the visible ceiling of a much deeper system. Below that stained rock lies the zone where chemistry, pressure, and structure decide whether gold is scattered or trapped. As iron minerals oxidize near the surface, they create what geologists call an oxidation cap. This cap acts like a historical record, but it also plays an active role. It changes permeability. It redirects groundwater. It creates chemical gradients that influence where metals can move and where they must stop. Gold does not dissolve easily, but it can be transported in microscopic form when conditions are right. Slight changes in acidity, temperature, or fluid pressure can cause gold to drop out of solution suddenly, often just below the oxidized zone. This is why many gold deposits are found not at the rust itself, but directly beneath it. The rust marks where the system breathed. The gold marks where the system collapsed. In fractured rock, oxidation follows pathways created long before rust ever appeared. Faults, shear zones, and brecciated corridors become highways for fluids rising from depth. These same pathways later guide oxygen and water downward during weathering. When both movements align in the same structures, concentration happens. This is the quiet rule of geology. Where fluids move repeatedly through the same channels, value accumulates. Rust patterns help reveal those channels. A vertical rust streak cutting through otherwise clean rock often signals a fault or fracture that reaches deep into the crust. A broad rust zone with soft, crumbly textures may indicate altered rock where minerals have been chemically stripped away, leaving space for gold to settle. Hard angular quartz fragments embedded in rust-stained ground tell a different story. They suggest violent fracturing, rapid pressure release, and sudden mineral deposition, the exact conditions under which gold is often forced out of solution. These details matter because gold is not evenly spread even within a deposit. It pools, it traps, it hides in specific physical and chemical environments, and rust helps narrow the search. In desert environments, this relationship becomes even clearer. Low rainfall preserves oxidation features for long periods of time. What you see today may reflect processes that occurred tens of thousands or even millions of years ago. A rust-stained ridge in a desert is not recent damage. It is a geological memory. That memory tells you where fluids once moved upward, where heat was released, where pressure dropped, and where metals were forced to make a decision, move on or stay behind. Gold almost always chooses to stay. This is why experienced prospectors pay close attention to the transition zones, where red fades into yellow, where hard rock becomes crumbly, where quartz veins pinch, split, or abruptly terminate. Those are not random boundaries. They are chemical and physical thresholds, and thresholds are where concentration happens. What looks like decay to the untrained eye is often refinement in progress. Nature stripping away everything that does not belong, leaving behind what cannot be destroyed. Gold survives oxidation. Gold survives pressure. Gold survives time. That resilience is not just geological, it is economic, because the same qualities that keep gold intact beneath rust-stained rock are the qualities that have kept it valuable through centuries of financial systems, currency changes, and market cycles. Gold does not rely on trust. It does not rely on performance promises. It relies on scarcity and physical reality. And geology is the mechanism that enforces that scarcity. Understanding rust patterns is not just about finding metal. It is about understanding how value forms quietly, invisibly, and over long periods. Most wealth is not created in moments of excitement. It is created in systems that work slowly and predictably beneath the surface. Gold-bearing systems follow rules. They reward patience. They punish shortcuts. Rust is the surface expression of those rules. When you learn to read it correctly, you stop chasing randomness. You start following structure. You stop hoping for luck. You start trusting process. And that shift changes everything, because once you understand that rust is not decay, but direction, you begin to see the ground differently. You recognize that some places have already done most of the work for you, that nature has already concentrated value, quietly, precisely, and without urgency. All that remains is the understanding to recognize it. Gold is not loud. It does not advertise. It waits. And rust, for those who know how to listen, is one of the clearest ways it speaks.